All right, we got one other thing to do here in torsion. So what we've got is indeterminate torsion. And I pointed out before that there's analogies between torsion and the problems you do that have to do with normal stress and length and things like that. This is analogous to the indeterminate problems we did with the PL over AE equation, but this time we're going to substitute TL over IG, okay? So I'm on page 689 is where I'm at. So if you have a bar and two fixed supports and you apply a torsion there in the middle, you're going to twist the bar, okay? This is what's going to happen. Now there's two key relationships that we want to be aware of here if we do that. If I take that bar there and I apply this torsion, I'm going to start to try and pull it and make it rotate. Well, if these are fixed supports, they're going to pull back, okay, or torque back, you might say. I don't know what the right word would be there. So you're going to get reactive torsions here. And the relationship is pretty simple. It's the sum of the two reactive torsions on either side equals the applied torsion. Now the challenge is going to be figuring out what the two individual reactions are. So if this torsion here happens to be, whatever, 600 Newton meters, it's not like it's 300 on either side. You don't know what it is, and there's a number of factors that can affect that. So usually a part of the process here is to figure out what those reactive torsions are. And the one fact that we have to work with is that the sum of the two reactions equals what's applied in the middle. Okay, so that's kind of where you start with this, all right? Now, that is the statics, you might say. And you might remember on the axial stuff that we did with the PL over AE, that we had, sometimes we could get tricky relationships to get the statics done for those problems. In torsion, that's not the case. This is always what it is in torsion. You can't get that much fancier like you can with the axial stuff. It's just you've got a shaft with some sort of support on either side, and the sum of the reactions is what you apply. That's just all what it comes down to, all right? Now, that alone, of course, is not enough. That's one equation with two unknowns. That's what you get from statics. The other comes from torsion, from strength of materials. All right, now what's going to happen there if you take C and you apply a twist there, you're going to roll that down to C prime. So you're going to get a twist right there that rolls C down to C prime. And so that's going to be an angle of twist there in the shaft. Now, based on that, we're going to work through and figure out, how we can use that twisting there, that relationship, to figure out what those reactive torsions are at A and B. All right, now there's some things here that I kind of left blank, so my intention here was to have you fill in the relationship between those, because what we want to keep in mind is the difference between the angle of twist and the shear strain, which are both angles that occur in torsion. Okay, now the shear strain is labeled. Generally speaking, unless the torsion's applied right in the middle between A and B, the gammas are not equal. Okay, that's the general case. Now, if the gammas, the shear strains aren't equal, if you multiply both sides by G, that's not equal, and that means that the shears in the two sides, generally speaking, are not equal. So neither the shear strain or the shear stress are equal in the two sides, generally speaking. You can't just assume that. Okay. However, if you calculate the angle of twist, there's one angle of twist in there, and you can calculate it from two sides. You can calculate the angle of twist from A to C, and you can also calculate it from B to C. And those angles of twist are going to be the same, okay? And what they're going to equal is TL over IG. Okay. So what you can do is use this to get those internal torsions, because generally speaking, the length, it'll be dimensioned in some fashion, if you know the dimensions of the shaft, you can find I. And if you know the material properties, you can get G, okay? So what you can then do is find those internal torsions in the shaft, which we call T, of course. And those internal torsions equal the reactions, okay? So the TL over IG for AC is the same, will equal the TL over IG for BC, because when you measure that angle, it's the same angle. If you measure it from A to C, it'll be the same angle that you measure from B to C. So the thing that holds is the TL over IG for both sides. Okay? And generally speaking, based on the shaft dimensions and the material properties, you can get three of these things: the length, the shear modulus, and I. Okay, so that's the general relationship that's used to figure out these indeterminate torsion problems. All right. So, we good with that? So why don't we look at an example here? Now this example has a few things kind of thrown into it. So let's kind of work through this thing. This example is a little bit tricky, but it illustrates some good concepts that we might, things we can apply to other types of problems. So what we got here is the maximum allowable shear in the shaft is 70 megapascals. That material that we've made this shaft out of can handle a shear up to 70 megapascals, but no more. Okay? Let's figure out how much torsion we can apply at point C there to that shaft. So we got the shaft dimensions, the lengths, and the diameters. Why don't you find I sub P from A to C? So what's that moment of inertia from A to C? So it's a pretty simple calculation, just pi over 2 R4, right? I mean, it's on the formula sheet, solid shafts, no big deal there. You often end up using the scientific notation on your calculator because it's such a small number for metric. Now for English, metric you use in meters, so it ends up being a small number. In English, usually you use in inches, so it doesn't. Okay.
The negative 12, that 10 so.
What's that now?
Like 10 times multiplied by 10 to the negative 9.
Oh, negative 12.
Negative 12, I think it's 10 so.
Yeah, it might be, I'm not sure. I think negative 12 is being like really small. It's getting into. Yeah. So I don't know. I got negative 8, is what I got. But you could have had a bigger number to the left. So, and I don't even know what negative 8 is either. I don't think it's got it.
I was up by a factor in my conversion.
So we good? Pi over 2 times 0.01 because we want half the diameter. 20 millimeters is 2 centimeters, which is 0.0, and half of that's 0.01 meters. So 1.57 times 10 to the minus 8. Okay. All right, so there you go. Now this stuff is kind of standard drill. Again, if you remember those axial problems, we got into all these different possibilities for reactions and all that stuff. For this stuff, that's not really what you do, okay? Because it's pretty straight up. You've got 2 reactions and a load in the middle. That's normally how it goes. So what I'm going to do is, one relationship I guess I should put on here is, I should look at this and say, okay, I'm going to have this and that. So one relationship maybe I should have put on the top of this thing is that the reactive torsion at A plus the reactive torsion at B is whatever is applied at C. I mean, that's kind of the statics part, if you know what I mean. I mean, we know that. And now I'm getting ready to do the strengths part, and that is the angles are equal. The angle from A to C equals the angle from B to C, and those equal TL over IG. We don't have the torsions, but we got the lengths, and we just found I sub P, and we're given G. It's 10 gigapascals. So given that, we can set up that ratio. The torsion from A to C times 0.2, which is its length, over I over G, is equal to the torsion in BC times its length times its, or excuse me, divided by its I divided by its G. Now, I don't think I did this, but if I were doing this, you know, looking at it now, probably what I'd do, I go, okay, that cancels, and that 10 to the negative 8 cancels. I'd probably just do that, you know, make my calculation simpler. I didn't do it on this one, though. You get to the same result, but I didn't do it on this one, okay? Even though it would get you to the same place. All right, so that's, you know, looking at this, just standing here right now, that's probably what I would do on the calculations. So what you're going to end up with then would be what? 0.2 over 1.57? So that's 0.127. Oh, okay. Oh, right. Okay, so it's when I do it that way, I'm going to get 0.1273 AC, and then I'm going to take 0.5 and divide it by 25.13, and I'm going to get the 0.01989. So this is what I would have got had I done those cancellations that I'm showing you. It leads to the same result, however you do it, okay?
Is that because the moment where it's so small?
No, I'm just canceling equal things from both sides of the equation just to simplify it. I've got that equal sign, so algebraically I can cancel the 10 times 10 to the 9 on both sides. Yeah. And I can cancel the 10 to the minus 8 on both sides. I'm just doing a cancellation.
What about the 1.57?
Well, that stays.
Okay.
Yeah, that's staying as is the 25.13. So I'm just canceling the 10 times 10 to the 9 and the 10 to the minus 8. That's all I can cancel with that. Okay. And I'm going to get to the same result. And I went ahead and I solved it both ways. So I got TAC is 0.1562 TBC, or I could invert that and get TBC as 6.399 TAB. Okay? So what you have here is kind of the standard way you handle these. You got the statics, which I wrote up at the top of the other slide. You know, of course I don't have it here, but TRA plus TRB is equal to TC. That's the statics. And then down here I've got the strengths. And I've got two unknowns. I've generated two equations, so I can go ahead and, you know, start doing this thing, okay? Now, if I knew what TC is, you know, I would just go ahead and I would solve this thing out, but I don't, okay? Now, there's an extra step on this one because I don't know what the torsion at C is. So I got to work through the shears to get to that. I wasn't given what the torsion at C was. What I'm given is how much shear that shaft can take. It's 70 megapascals. So I got to work with that a little bit to figure out what that torsion is going to be. All right. All right, now the relationship I work with that is that the shear is TR over I. So what I can do is I can plug in the 70 into that for both sides, the left from A to C and the right from B to C, and find how much torsion either side can handle before it maxes out with shear. Okay. So I'm solving that relationship that tau, the shear stress is TR over I. I'm solving it for the torsion. It's tau I over R. I'm going to plug both of those in. And that's the torsions I'm going to get for either side. Okay. I'm having to do this because I don't know what the TC is yet. I've got to figure this out. So what I'm doing here is I'm plugging this stuff in, and I'm seeing what the torsions would be in AC to cause a shear of 70, and I'm seeing what the torsion would be in BC to cause a shear of 70. So if the torsion in AC is 110, the shear in AC would be 70, and that's as far as I can go. As far as, I can't go apply any more torsion than that, or have any more torsion than that. Same thing on the BC side. If the BC torsion goes up to 880, the shear on the BC side will be 70. Okay. So kind of the way I think about this problem is I've got this shaft and I've got a pipe wrench on it, and I just keep applying more and more force on that wrench and pulling this thing around and around and around further. And at some point I got to stop because I'm getting too much shear. And I'm figuring out where I got to stop. That's kind of the idea of this problem, okay? Yeah. So I've got that shaft in there. Which is kind of like that, right? Got one line too many. Yeah, there we go. And then I'm going to put a pipe wrench on here, like so. And then I'm just going to start pushing on that pipe wrench and twisting that thing. And eventually I got to stop because I've got too much shear building up. That's what's going on. Okay. And what I just figured out is how much torsion each side can support until I got to stop. And this one is at 110 Newton meters, and this one is at 880 Newton meters, okay? But the problem I've got is that these are not gonna occur at the same time. I gotta figure out which one hits first, okay? And there's different ways to approach this problem. That's how I figured I'd approach it. So I gotta figure out, if I keep pushing on that wrench, when will either is the important word, of those values be reached, okay? So if you're putting this into your notes, make a note here because it might confuse you later. However, the 110 Newton meters and the 880 Newton meters will not occur simultaneously, okay? I have no idea how to spell simultaneously. That's my best guess. Is it? Am I good? All right. You know, the original journals of Lewis and Clark, if you look at some of those pages, they spell the same word 3 different times on the same page. So those guys are my heroes, you know. I thought, I always thought spelling should be a creative subject myself. I think that'd be better that way. English spelling makes just zero sense. There's this whole history behind how it was developed.
Didn't we take out a lot of letters because it costs so much money?
I think that was part of it, yeah.
Message sending, like they charged by the
by the letter?
not writing,
Oh.
you're sending, especially when telegrams came around, so a lot of words end up like pulling the U out of words like color. Even in the UK, they still have a lot of
Right.
spelled letters.
Right, yeah. That could be part of it, yeah.
Starting using these, so that's.
I know they brought the presses over from mainland Europe, and there was some letters in the Old English language that weren't like in French. They didn't have those letters, so they just substituted a couple letters. They did a lot of funny stuff. I mean, it's kind of bizarre, really, how we spelled it. Anyway, but I guess I'm getting off the subject. So what we got to do here is figure out which one maximizes first, okay? So now I know that TAC max is 110 and TBC max is 880. Now I got to figure out which one maximizes out first. So I know that TAC is 0.1562 times whatever TBC is, and that's 880. So I'll put that in there. And I know that TBC is 6.399 times whatever TAC is, and that's 110. So I'll just pop those in there, okay? And I'm going to see from doing this little analysis here which one maxes out first. What I did, I generated the 110 and the 880 based on those shears. Okay, but the shears are independent of the fact that the two shafts are connected together. That's independent, okay? Now I'm going to check and see which one maxes out first. And the way I do that is I use that torsion relationship with the angle, the TL over IG relationship, and the ratios that came out of that. So TAC is 0.1562 times whatever TBC is. Well, if TBC goes up to its maximum, TAC will be 0.1562 times that. It'll be 137.5. And see, that's too big. Okay. On the other hand, if I push AC to its max of 110, TBC is 6.399 times that. That's 704. That's okay. All right. So if I start pulling on this wrench that I drew, what's going to happen is this side maxes out first. And when that hits its maximum, that isn't 880, it's 704, which is still within tolerance. That's still okay. Okay? So what's going to happen is the left side, AC, when it hits 110, the right side is not yet to 880, which is good. It's only at 704. Okay? So that's what's happening. So this problem required a little bit of extra analysis to kind of work through that. You okay with that? What's going on there? You can do this different ways. This is how I'm doing it though. Okay. All right, so I got 110 from A to C and 704 from B to C. So that means the torsion applied at B is the sum of the two. It's 814 because I know whatever's in the middle will equal the sum of the two reactions. So what's going to happen here is I can apply a torsion at C of 814. When I do that, the reaction at A is 110 and the reaction at B is 704. That's how that 814 gets split to the two sides. And when that AC is at 110, I got to stop. I can't apply any more torsion because it's hit its maximum shear when that happens. That's what's going on here. So there's a couple different things happening at once. All right. Got any questions on that? So that's the deal with that one. So that's indeterminate torsion. So it's similar to the axial stuff we did in that you can do a little bit with statics, but you're limited. So you can do more when you employ strength materials. You can solve for an extra variable is usually how that works out. So how about doing 311 and 12? And those will be due Friday, I think. And that'll be the 21st. Are we good with that?